Okay, this video concerns 9.8, which has to do with what they're calling arguments here. It really is the introduction of the last connective that we have between two statements. We started out with and or, we used negation, things like that. And if you looked at that table at the beginning, it also included this symbol, which they show for the first time on this page. But first they define an argument as any set of compound statements or compounding that includes this symbol, this implication. Now, actually, an argument comes up a little bit differently defined later on. That's in the next video. So this is a pretty general definition, and I've seen it defined more in terms of what we see in the next video, more generally. But in this context, we're talking about anything that involves this arrow. So here's the truth table for it. It is P and Q, and you've got truths and falses, and there's the definition of what this arrow means. It's also in the formula sheet. And it's right here in this column. So let's analyze that. I want to look at it and talk about it a little bit. And let's look at it right here. Let's go ahead and I'll make it up a little bigger if we start with P and Q. And then we're going to look at P implies Q. P implies Q is how we say that. Or we can say if P, then Q. That's another way to say it. If P, then Q. And we can put a comma between them. If P, then Q. So this is the implication. Sometimes it's just a regular arrow without the double bar in the middle, but the book uses the double bar, so I will too. Okay, so we'll start our truth table the way we always do, looking at every possibility of T's and F's, truths and falses for P and Q. Okay, now here's the definition of the implication. If you say, just like a father might say to their kid, if you clean your room, then you get to go to the movies. Okay. We want that, we're going to analyze that statement. So if that statement is true, if that father is telling the truth, if the father is reliable and a good father, does what he says, then if the student or the kid cleans their room, then they get to go to the movies, then the implication is true. All right, now, what if they clean their room and then they aren't allowed to go to the movies? Well, that is, then the statement that the father made is false, because he said if you clean the room, you can go to the movies. Now, the hard part, the weird part, is the second half of this table, where the first part of the implication, what they call the antecedent, is false. What happens then? What if you don't clean your room? Well, the father said, if you clean your room, you go to the movies. If you don't clean your room, anything can happen, and it won't make the father a liar or a bad guy. If you don't clean your room, you might go to the movies, or you might not, but it doesn't make him a liar either way. So in fact, what we say is those get truths in the implication. The only way it can be false is if the antecedent is true and the consequent is false. If I say P implies Q, I have P and then Q doesn't have a truth, then the implication is false. So takes a little getting used to. The other thing to realize is like the language we used before for ands and ors, the implication's easy to make true. The implication's always true whenever the antecedent, the thing on the left, is false. So usually if I see that in the table, those are what I'll fill in first. Then I go back and everything else is true for the antecedent. I look for only true consequence and give them a T, and only false consequence give me an F. So this mirrors this column, the consequent column, whenever the antecedent is true. We'll see that in an example, all right? So let's keep that in our minds. It's on the formula sheet and in the book on that page we saw before. Okay, there's the formula sheet version. And here's the text version. Okay, and what I'm going to do is I'm going to go forward and look at 9. Before we do that, though, let me tell you one more thing. That another way to look at if P, then Q in terms of sets. P implies Q. So in set theory, we use a capital P. And what I'm going to say is that that is a subset of Q. It kind of looks like an arrow, but it's pointed the wrong way here. But what we're really seeing here is that if you have a set P located entirely within a set Q, that's the example for sets of implication. If it's in P, it's automatically in Q. If it's not in P, it could be Q or not. And if it's not in Q, it's definitely not in P. So all these things kind of help us figure out the logical part of the implication later. So if you keep this diagram in mind for sets, it can help you understand the way that things work for logic. Okay, now let's go forward and we'll look at an example. All right? We're going to look at example 9I, page 403, number 5. So we're going to look at 9I, number 5, page 403. All right, and just to make things nice and neat, I've got a nice 2-column truth table here. Let's write down what 9I is saying. All right, 9I says to do the following. It's going to show, does P and Q imply P, or P implies P and Q? Okay, I'm going to straight mark there. All right, that's page 403. We're going to test this and see if this is a tautology, contradiction, or neither. All right, so the first step is I have to build this up. So I'm going to look at P and Q first. Okay, P and Q. Well, we know from the elementary truth tables, P and Q are only true when they're both true. If any of them is false, it's false here, so we should get in the habit of doing that pretty quickly. Now, I'm going to say, I want to look at where this implies P. So I'm going to call that 1. I'm going to say, where does 1 imply P? Okay. Now, remember, if the antecedent is false, the implication is automatically true. Now, in what's left, the antecedent is true. Is the consequent true? Yes. Okay, so this is a tautology right here. This one's always true. All right? And so actually, if I think ahead, I'm going to disjunct this with anything else. If this is always true, the disjunction is going to be true as well, no matter what. But let's finish it out. But this part, this half, is a tautology. Now, let's go on. Let's look at this one. I want P implies P and Q. Now, I already got P and Q here, and I have P here. So now what I'm talking about is P implying column 1 here. Does P imply this? Once again, I go over here, anywhere that the antecedent is false, I get an automatic true. Anything on the left-hand side of the implication is false, I get an automatic true. By this time, you might be wondering, could we have the arrow pointing the other way? You could, but we just hardly ever do that to make sure it's clear, so that you can read it left to right, and the antecedent's on the left. It's just normally done that way, just like the subset symbol is almost always drawn with the subset first. So we keep to that convention if we can. All right. So I automatically get a true here. The other ones are left true. So now I look at the consequent here. Anywhere it's true, this is true. Anywhere it's false, it's false. Okay, so this one is not a tautology. Now, I want to number that column, this one, and this one, because what I want to do is I want to conjunct them. So I'm going to say this is column 2, this is column 3, and I'm going to look at 2 or 3. It's an easy one to fill in, because 2 is always true. And in a disjunction, if either one of them is true, the disjunction is true. So this is automatically true, and it is a tautology. Okay, in other words, I've built a tautology out of a tautology disjuncted with something else that isn't. But this is a tautology. So that is the answer to that. And that one's completely all the way there. All right, so that concludes that problem, and that shows you how to use implication in a truth table.